let me come around real fast. Okay. I don't know how sensitive this thing is. Well, yeah, we're live. We're on. So, hi everybody. Welcome to the Test 6 review session. My name is Mr. Martin. I'll be your spiritual guide. So first and foremost, this is going to cover modules 10 and 11. So that'll be magnetism and waves. This is probably the one test where it's like two very distinct different things that are all just piled into a test together because, that's that. So let's start with magnetism because that's been the longest. Typical convention for magnetic fields in general is that they go away from the positive and toward the negative. And technically, they continue through the south to the north as magnetic field lines are continuous inside of it. But if you get to the outside of a magnet, just exiting the north, entering the south, and that's just convention. Kind of like we came up with the convention for the electric field to just be the force, well, a depiction of the force that a positive charge would feel. We just kind of decided that. We did the same thing with the direction for the magnetic field. But once you stick it, you are stuck with it. In general, more field lines that are drawn, the stronger the field. I'm probably not going to test you on that because we didn't really do a whole lot about that. But that's just something that could be kind of fun and good to know. This last little note right here, again, I'm probably not going to test you much on, but it's probably good to know. No magnetic monopoles exist. What I mean by that is an object that's just a north pole or just a south pole. It's kind of weird. If you take a bar magnet and cut it in half, you end up with two small bar magnets, each with their own north and south pole. Which is kind of funky. And you can continue to cut it in half over and over and over again. Doesn't matter. You never get a magnetic monopole. Actually, physicists, well, last time I read up on it, which was a few years ago, still didn't fully understand this. And this is an area of heavy research. But I need to brush up on that just to make sure. I'm just going to hang out with people. I still see people writing, so I don't want to move forward. Okay, now I want to move forward. So the very first thing that we talked about that involved a little bit more rigor, I guess, was the magnetic force on a charged particle. So I showed you all a video about how magnetism is simply caused by the movement of electrons in the first place. So electricity and magnetism are very, very, very closely related. If you have a charged particle electrically charged and it moves through a magnetic field, it feels a force, simply because electricity and magnetism are kind of two sides of the same coin. That force is a vector, like each and every force that we've ever talked about in class. And vectors have both magnitude and direction. So this vector, this force, is determined by a charge, that's just a scalar, multiplied by a cross product, a vector cross product of V cross B. With a vector cross product, you take one vector, take another one, cross them together, you get a third vector out of it, and that's what the force is. Like I mentioned before, all vectors have magnitude and direction. So with cross products, you can find the magnitude as vector 1 times vector 2 times the sine of the angle between them. In this case, that simplifies down to just Q times V times B times the sine of theta. And theta is defined as the angle between the velocity and the magnetic field. So it's kind of weird if you have, let's say, a velocity going to the right, so a charged particle with a velocity going to the right, through a magnetic field that's pointing to the left, that charged particle feels literally no force because theta would be 180 degrees and the sine of 180 degrees is 0. Same thing if it's in the same direction. So if I've got my magnetic field pointing to the right, as well as the velocity pointing to the right, the force that particle would feel is 0 newtons. So it would just keep on trucking as it's been trucking and no big deal. The most force that you can get out of this is when theta equals 90 degrees. That's when you get your maximum force. So I'm going to get a lot more force if I have a velocity moving to the right through, let's say, a magnetic field that's upward. That's going to be a lot. Otherwise, I can just take my velocity vector. Let's say my magnetic field vector is pointing up and to the right, I guess, like this. Theta would just be this angle here, the angle between the field lines and the velocity there. Yeah. Yes, I have a question. When you use the sine of theta compared to not using it, if you're finding a value for the force, you should always take it into consideration. QVB sine theta. A lot of the examples we've been dealing with are when theta's at 90 degrees, and the sine of 90 degrees is just 1. So the examples you're thinking about, which are just simply Q times V times B, that's when theta is at 90. And that's a lot of examples that we do. So yeah, those times that you thought we were ignoring it, we really weren't. I was just kind of breezing over the sine of 90 equals 1. Yeah. Any others? Cool. So that's the magnitude. The direction you can find with the right-hand rule. I wouldn't recommend necessarily writing down each and every word of this slide because that's a lot of words to keep track of. All you really need to know is that your fingers equal the first vector. So in this case, that's velocity, because V cross B, all times the charge, will give you that force. So the first vector there is velocity. They get your fingers. Your palm points in the direction of the second vector. Well, the second vector in this case is the magnetic field. That'll be your B value. And then your thumb is the resultant. Well, QV cross B results in a force. So the force is the resultant. That gets your thumb. Sometimes I'll give you the first two, the velocity and the magnetic field, and ask you about the force. And sometimes I'll give you something random. I'll give you the velocity and the force and ask you for the magnetic field or something like that. So just be aware of which part of your hand goes with what when you do right-hand rule stuff. Yeah. And don't forget, did I not include this? Hold on a second. Let me just look. Okay, good. It is here. Never mind. I thought I'd forgotten it. So here's kind of a little picture of what's going on. This person has moved their second finger to be in the direction of that magnetic field, but that's the way the palm is facing anyway. So in this case, vector A represents the velocity, vector B represents the mag field, just as B does, and C is the force. Yeah, beautiful. You do need to recognize these symbols. I'm not necessarily going to tell you directly what it is. So out of the page looks like a little arrow pointing towards you, coming out of the page. Into the page looks like the feathers of an arrow going into the page away from you. Meanwhile, up, down, left, right, they are all also arrows, but those are a lot easier to draw and imagine. You've got up, down, left, and right. Those are pretty much the only directions I'm going to ask of you. Fun fact, when you're doing these vector cross products, a lot of times you may have up to 6 multiple choice options. You can always eliminate all but 2. All 3 of these vectors have to be perpendicular. Well, no, that's not true. The velocity and the magnetic field don't have to be perpendicular, but the force has to be perpendicular to both the velocity and the magnetic field. The resultant vector is perpendicular to both the incoming vectors. So if I have, let's say, a velocity to the right through a magnetic field going into the page, then automatically I can eliminate, for the direction of force, 4 of those. Because the velocity is going to the right, the force is not going to be right or left because it needs to be perpendicular to the velocity. Because the magnetic field's going into the page, the force is not going to be in or out because it needs to be perpendicular to that magnetic field. So that means the force would only be up or down. Then you have to use the right-hand rule to figure out which one, but you've already brought a 1 in 6 chance up to a 1 in 2 chance, which is a lot better in case you get that right-hand rule wrong. So look at the directions incoming for velocity and magnetic field and immediately eliminate the same direction or 180 degrees away from it. And that should help. Should help a lot. Negatively charged particles. I've mentioned in class a few times. They are in the exact opposite direction as the positive particles. So you could use the right-hand rule and just remember to swap your direction by 180 degrees. So if the right-hand rule says left, the correct answer is right for a negative particle. If the right-hand rule says into the page, the correct answer is out of the page for a negative particle. Or if you prefer, you can just use your left hand instead of your right hand. The moment you see keywords like negative or electron or something like that, then just remember to use your left hand instead, and the left hand will give you exactly the proper answer, which just happens to be 180 degrees away from what your right hand would do in that instance. Then we came to this. We did an activity today involving, well, not really so much an activity. I asked you a series of questions on Socrates, Canvas. And I found that a lot of people had forgotten this one. So this is going to be the force on a current carrying wire due to an external magnetic field. So we've not yet gotten to the part where a wire is producing a magnetic field. That's going to come later. This is a wire is running through a magnetic field that is coming from somewhere else. The force on that wire is going to be equal to, well, that's F right there is the force of the wire, on the wire, in newtons. Oh, come on. I is just the current running through the wire in amps. L is going to be the length of the wire. That's in meters. And B is the magnetic field going through the wire. From somewhere else. And that's going to be measured in units of Tesla. So these are all just base units right here. So just like the other cross product, QV cross B, this one produces a force that has magnitude and direction. The magnitude is just the current times the length times the magnetic field times the difference in angle, or the sine of the angle, between the current and the magnetic field that it's going through. So far, a lot of times that's just been 90 degrees to make things a little bit less complicated, but it's the same sort of deal. Then you're going to use the exact same right-hand rule to figure out the direction of the force. This time, your karate chop fingers are the current because that's the first vector that's showing up. Your palm faces the direction of the magnetic field, and your thumb is the direction of the force. So it's the exact same right-hand rule. And if you think about what's going on inside a wire, it is just a bunch of charged particles moving. Right? So you could treat it just like a QV cross B. They're moving with some velocity in the direction of the current. So do a QV cross B right-hand rule on them, and it's the exact same thing. Um, so IL cross B and QV cross B is actually the same rule. It's just zooming in on a single charge or zooming out to look at the overall wire that these charges are moving through. But that's the only difference between these two equations. Questions, or are we good? I have one thumbs up, so we're moving on. Oh, now I have two thumbs up. The force is up. Oh, yeah, the thumbs up means the force is up. That's exactly what it is. The force is up. All right. So, so fun story. Not only are wires affected by magnetic fields, they also make magnetic fields. So it kind of goes both ways. If I feel a magnetic field, I feel a force. But as I'm doing my thing, I'm also making a magnetic field that all the other wires around me can feel. So when you're looking for that, this is the magnetic field produced by a straight wire. That's simply going to be mu naught I over 2 pi r. The most common mistake in this one is figuring out that r value. So let's say I've got a current in a wire, and that current's running directly upwards. From the second right-hand rule, which I'll talk about just a second, I produce a circular magnetic field, which I'll draw in blue, that loops around the wire. Hey, that was pretty good. If I pick a single point, let's say I pick a point that's, I don't know, half a meter away from the wire. One tempting thing to say is that, well, this point that's half a meter away from the wire, a lot of people want to say that's going to be a diameter because that's the raw distance, but it's not really. The circle that's produced where the magnetic field goes through that point also loops 0.5 meters on the other side of the wire as well. So it is a radius of that circle. Basically, you can just define r as whatever the distance away from the wire where you'd like to measure. At this stage, I probably shouldn't say where you'd like to measure. I should say where you're told to measure. Everyone has fun with magnetic fields and wires. And that's going to have to be converted to meters. Yeah, B is magnetic field. So this is the strength of the magnetic field produced in Tesla. And I is the current in the wire in amperes. Cool. So what's really happening is you can imagine just a series of rings all around this wire that get weaker and weaker as you go out away from it, is basically what's happening. So I just drew one circle on there just for ease of viewing. There are really smaller circles that are stronger. There are wider circles that are bigger, all around that one point of the wire. And then it's all around all the points of the wire. So really the magnetic field's forming more of a cylindrical shape around it. But Don't worry too much about that. That's fine. To figure out the direction, you're going to use the second right-hand rule. The way the textbook introduces these and the way that I've learned them ever since I started learning this uh, was a second and third right-hand rule. To me, those are very, very, very similar. When you've got a straight wire, then the magnetic field you produce around it is a series of circular shapes. Oh yeah, here, this has drawn the picture of the different rings around it. That's pretty nice. Um, circular rings around it. So that means the thumb is going to go in the direction of the current because that's in a straight line. You'll start with an open palm and close your fist. The direction that your fingers curl as you close your fist will at least get you started in the direction that that the magnetic field is circling around this wire. And that works for any straight wire with conventional current. But those are not the only types of wires that can produce magnetic fields. You can also get a magnetic field from a solenoid, which is a series of loops of wires. So this is specifically the field strength in the center of the solenoid, which is really what we typically care about when we're using these things. These are used for electromagnets, for MRI machines, for a whole bunch of things. So with the electromagnet, you care about the strength of the magnetic field going through the nail that you're trying to magnetize or something like that. For the MRI machines, you care about the strength of the magnetic field inside the machine, not necessarily outside in the room. So to get that, it's just going to be mu naught times n, where n is the number of turns of coil. So if there are 500 loops, n is 500. L is the total length inside the loops. So a reminder of what I mean by that. If I've got a coil of wire that runs up here, and it loops, and it loops, and it loops, and it loops, by L, I don't mean the total length of wire that was used to make all these loops. So this could be like 20 meters, 30 meters, whatever else. But once you finished wrapping it, and then, oh, whoops, I just deleted the whole thing. There we go. So once you finished wrapping it, and the wire comes away from it, there. L is just the raw length from the very start to the very finish, right there. So basically what this is saying is the more loops that I can get with the least amount of space that it takes up, so the more tightly compressed the loops are, the higher of a magnetic field I'm going to get. And good old mu naught is still 4 pi times 10 to the negative 7. That's just a constant called the permeability of free space. That constant I'm going to give to you on the test, so you don't necessarily need to know that, but you need to be able to use it. But 4 pi times 10 to the negative 7 Tesla meters per ampere is mu naught. And I is the current going through it. In amps. All right. Well, in this case, when you produce a magnetic field from a wire that's looping in a bunch of circles, you'll use the third right-hand rule to figure out the direction of that magnetic field. The third right-hand rule is pretty much identical to the second, with one exception. In the second, you had a straight wire and a circular magnetic field. Here, you've got a circular wire and a magnetic field that goes in a straight line through it. So the trick is just wrap your fingers, curl them in the direction that the current is curling, and your thumb is going to point in the direction of the magnetic field. But remember, this is the direction of the magnetic field that's running through the middle of the solenoid. So in this image, the thumb is pointing to the left there. That means the current is running through to the left. In the middle, when it comes out, then it just acts like a bar magnet. So it exits the North Pole, loops back around, and enters the South Pole. It would be this sort of a shape that's being formed. As the overall magnetic field around here. So if I suddenly reversed polarity and sent current running the other way, I would swap which side was the North Pole and which side was the South Pole for this solenoid, basically. Any questions about third right-hand rule or second or? Cool. So I mentioned this before. I've got it up on a slide here. But they're very similar. You got two parameters to worry about, current and magnetic field. One's a straight line, that gets your thumb. One's traveling in a circle, that gets the curl of your fingers. And that's all you really need to know about that. Then we wrapped up magnetism talking about Faraday's law. This may be the single, well, I don't want to say that, but it's a very important equation in physics. Because quite frankly, this is how a lot of our electricity is generated. You somehow change the orientation of a magnet relative to a coil of wire, and you produce a voltage. With a voltage, you can get an electrical current out of it. So the equation looks actually a lot more complicated than it is. So the voltage that's produced, which is going to be measured in volts, is signified by this little epsilon. The epsilon just means EMF. It's basically a power source, and that's what's produced. N is the number of turns of coil. So once again, the more turns in the coil that you have, the more you're going to get out of it. In this case, voltage. In the other case, magnetic field. Now, here, this little phi with a subscript b, that's what's known as magnetic flux. So magnetic flux by itself is just the strength of the magnetic field at the center of the loop of wire, whatever the value is there, times the area of the loop of wire. By the area of the loop of wire, I literally just mean, here, let me highlight it. Whoops. Come on. This circle right here. The area of that circle is your cross-sectional area. And theta is the angle away from 90 degrees. So here's what I mean by that. If you've got a coil of wire, like here, and I've got a magnetic field approaching it directly this way, then theta is 0. And the cosine of 0 is 1. And that's great. If I have the magnetic field instead approaching, let's say, like this, then theta is going to be whatever the angle is away from my 90-degree mark here. What that tells me is if I try to send a magnetic field, like let's say directly above it, going this way, then I don't get any voltage from that. Well, then I don't have any magnetic flux actually at this point. Sorry, not that I don't get any voltage. If I then like spun the wire, I could get a voltage out of it. But yeah, so there are actual multiple ways of getting voltage. You can move the magnet closer to the coil of wire. You can move the coil of wire closer to the magnet or farther away, closer or farther away. You can spin one or the other in certain orientations. I could collapse this coil of wire because then I'd be changing its cross-sectional area. So that'll change the flux. Basically, as long as one of these three items is changing, then I get a change in the flux. So it could be the strength of the field at the middle of this loop. It could be the cross-sectional area of the loop, so I can expand or contract the loop. Or it could be the angle between them. I can kind of shift them or twist them relative to each other, and I'll get it that way. But once you figure out the magnetic flux at first, then the magnetic flux after something happens, after there's some sort of movement, um, delta magnetic flux is going to be that change in magnetic flux. If you remember from fall semester, anytime there's a change, I can set that equal to my final flux minus my initial flux. And that's your change. Um, so a lot of times you'll see problems where the magnetic field strength at the center increases from 1 Tesla to 4 Tesla, but the area stays the same and the orientation stays the same. So then magnetic flux would just be 5 minus 1 would be my change in magnetic field, all times the area, all times the cosine theta, and there's my delta phi b. And delta t is the amount of time it took for the magnetic flux to change. So the faster you do it, the more voltage you're going to get out of it. Ooh. And that's Faraday's law. So a quick summary, and I'm just going to breeze through this. If you have already existing magnetic field near some wires or charged particles, you can calculate how that magnetic field affects the wire or charged particle. So if it's just a charged particle, F equals QV cross B, that's the force that the particle feels. If it's a wire, F equals IL cross B, that's the force the wire feels. And if you've got a loop of wire and an already existing magnetic field, then I can generate a voltage with that as negative N times the change in flux over time. Oh, and by the way, this negative right here, don't worry too much about it. That basically tells me the direction of the current as a result. So yeah, you'll get a certain voltage. Basically, if I would expect, let's say I increase a downward magnetic field through a coil of wire, looking at it from above, I would expect it to create a current going clockwise. That negative means it creates a current going counterclockwise. Which actually produces an opposing magnetic field. So that negative is basically just telling you that the universe hates it when you try to change something, and it will create an opposing thing. It's why when I do the ring launcher, that little piece of metal is shot up away from the coil of wire rather than attracted downward toward it. It's repelled rather than attracted. It's also why when you drop a magnet through an aluminum or a copper tube, it goes really, really, really slowly because the current that it's creating is producing a magnetic field to repel it. That's all that the negative is. So, yeah. So this page was all about how existing magnetic fields affect wires and charged objects. This one is about how wires produce magnetic fields. If it's a long straight wire, mu naught I over 2 pi r, and you get a circular magnetic field. If it's a solenoid, which is a loop of a wire, circular wire, B equals mu naught Ni over L, and you get a straight magnetic field. And that's it. Whew. So that's what you need to know for magnetism. Cool. Then we started talking about waves. So make sure you know a few simple wave terms. Wavelength is the distance from crest to crest, or trough to trough, or midpoint to 2 midpoints over. Basically, it's the distance that a wave travels before it starts to repeat the same motion over again. Once it repeats the same motion, then you're onto a new wavelength. Amplitude, which we've not talked a whole lot about, is the height up from the midpoint to a crest or from the midpoint down to a trough. If you tried to measure from a trough all the way up to the crest height, that's technically 2 amplitudes. So just be aware of that. If you're thinking about it in terms of a standing wave, it would be the difference in height from a node to an antinode. There are a few different types of waves. This is when I had my wave machine with my gumdrops up here. There's transverse. That's where you have your crests and troughs. And the The main point of import here is that the particles have motion perpendicular to the wave motion. So on my little gumdrop machine, I could send a pulse to the right or to the left, but the gumdrops themselves would just move up and down. Hey, that's fine. It's a musical interlude. I like it. But we could talk about resonance. Meanwhile, longitudinal waves consist of not crests and troughs, but compressions and rarefactions. So, a compression is a region where the medium is way close together. Oh, what just happened? There we go. Like here. A rarefaction is where the medium is really spread out. Here. For waves like these, the motion is parallel to the motion of the pulse. So the particles would move backwards and backwards and forwards while the whole pulse moves forwards. In this case, a wavelength would be from compression to compression or from rarefaction to rarefaction. And this is what a sound wave is, for example. So transverse would be a light wave, longitudinal would be a sound wave. Quick official timeout while people write stuff down. When I was at Virginia Tech, I always remember this. If one of our games was being nationally broadcast, there was always this guy in a red windbreaker. And if he stepped out on the field, that was an official timeout, which basically just meant they needed to go to commercial break. And that was the worst when you're in the stands and you're getting like all like hyped up and your team has the momentum. And then all of a sudden the guy with the red jacket steps on. Oh, I hated that guy because he would break the team's momentum and we would just be. Anyway, so pretend like he's standing there right now. Oh, I'm being booed right now. Yeah, that's true. I don't have a red jacket. Boo to boo to that guy. These are just general terms that you need to know, as well as some symbols that are associated with them. The main area of difficulty that a lot of students run into is telling the difference between the period and the frequency of a wave. And they're actually direct inverses of each other. So the period is just the amount of time it takes the wave to travel one wavelength, or the amount of time that passes before, like let's say I see a crest move past my finger. It's the amount of time that passes until I see another crest move past my finger. So just the raw amount of times in seconds. The frequency is the number of wavelengths that pass a given point in 1 single second. So period is seconds for one wavelength. Frequency is wavelengths for 1 second. Wavelengths for 1 second. So if I've got my stopwatch running, I count the number of crests that come by my finger, and then I stop it at exactly 1 second. That's the frequency. If I've got that count, how many times per second did it happen? Then you've got a wave speed. That's how fast the pulse is moving. That doesn't necessarily mean the particles in the medium. So when I say something's, I've got a wave speed of 5 meters per second, that doesn't mean that my gumdrop moving up and down is moving at 5 meters per second. In fact, because it's moving up and down, it's speeding up and slowing down and speeding up and slowing down over and over. But the pulse can hold a single velocity as it moves through. And the wavelength, denoted by one of my favorite Greek letters, lambda, is the distance until the wave repeats itself. Crest to crest, trough to trough, midpoint to 2 midpoints over, something like that. Guy in the red jacket is back for just a little bit. Please hold. he stepped off the field again. He's doing it way faster than usual. So in general, for pretty much all waves, just remember these. F equals 1 over t basically just means the frequency in hertz is just 1 over the period in seconds. So again, be very careful not to mix up these two. This one right here, I'm going to go ahead and, I'm going to circle it with a yellow highlighter. Because this one is a beautiful equation for waves. That is the velocity of the wave. Remember, not the particles in the wave, but the wave itself in meters per second is equal to the wave's own wavelength in meters times the frequency in hertz. And that's it. Hey, since the frequency is also 1 over the period, I could also rewrite this as v equals lambda over t, and that would be the exact same equation. But that is one that you're going to need to know. It works for every single wave. A pulse on a string, a sound wave, a light wave, you name it. V equals lambda f is where it is at. And by the way, I'm sure you all don't remember this, but back in August, we were just learning units and dimensional analysis. I gave you the units of wavelength, frequency, and velocity and had you put this equation together for me just based on the units. And I was like, yeah, so hang out until April or whenever when we do waves, and that's gonna be that. And then it came true. I'm not a liar. So if you see a couple of pulses that meet each other, you get what's called superposition. Pretty much just a fancy word to describe constructive and destructive interference. So if a crest meets a crest, then the amplitudes will add and you get mega crest. If a crest meets a trough, then trough meets a trough, the amplitudes add and you get mega trough. But if a crest meets a trough, then they decrease the overall amplitude. If the crest happens to have the exact same amplitude as the trough it's meeting, it will cancel entirely to 0, just for a brief moment. Actually, after this happens, the two pulses continue to pass through each other. It's weird, even after destructive interference. So I've got a crest coming one way, a trough coming another. They meet and cancel, and then they move past each other and have their own amplitudes again. It's crazy, man. But for that moment where they're trying to occupy the same space, you get constructive or destructive interference. I mentioned here in both cases, amplitude vectors add. Basically, all you need to know from that is if I've got the amplitude of one pulse, A1, and the amplitude of another pulse, A2, if one is down and one is up, adding a down vector to an up vector means you subtract. Adding an up vector to an up vector means you add. Adding a down vector to a down vector means you add as well, but they're both downward. So that's what I mean by that. We started making waves on strings. That was fun. So the velocity of the pulse that you send is going to be the square root of the tension times the length divided by the mass. Let me look at something real quick. Okay. The way that I've been writing it in class has been this. If you take the linear mass density is equal to m over L, just mass per unit length. That's going to be equal to the letter mu, which I hate because it's a metric prefix and is also part of the constant in magnetism, the permeability of free space. I don't know. I guess physicists really like mu because they use it a lot. Then I could rewrite this equation as V equals the square root of F over mu. But it's the exact same thing as the equation up here. So either way you write it, I am perfectly happy. Ah, because mu is in the denominator down here. So f over mu would yeah, would go down to this, and that's the same thing as, yeah. Okay. Then we talk standing waves, and this is what we've been doing lately, so you know we're kind of sort of getting to the end of this. Um, the standing waves are just when you send a series of pulses, they bounce off one end and come back and start to interfere with each other. Um, if you happen to be pushing it at exactly the right frequency, you get a wave that looks like it just moves back and forth from crest to trough, but there's no forward or backward pulse motion. Um, Even though there really is, it's a lot of forward and backward pulse motion. It just happens to be interfering with itself to the point um, where you don't see it. And that's why it's called a standing wave. Um, so you end up with ultimately no forward velocity. Here's where you get nodes and antinodes. So, a node is no motion. Node's not moving. Antinode is anti not moving. So, lots of moving. I don't know. Anti nothing. So, you're going to want to be familiar with just some of the harmonics patterns. And I've already posted this PowerPoint onto Canvas as well. So you may just want to go in and copy that down. Don't forget, you're also going to need to know how to figure out how many wavelengths are fitting on there. Um, and there's a few ways of doing it, but for each one, you should be able to tell me how many nodes, how many antinodes, and there's a wavelength and a half, or a single wavelength, or just half of a wavelength. Um, So you'll need to be able to do that. So make sure you've got those images down, not just for closed at both ends, you're also going to need it for open at both ends. The only difference between closed at both ends and open at both ends are where the nodes and antinodes are falling. On your closed end, you get a node. On your open end, you get an antinode. Um, and that's about it. So it affects the number of nodes and antinodes in each harmonic, but it doesn't really affect how much of a wavelength you're fitting. So on the guitar front, if I go from one node to the next, that's a half a wavelength. So I would say the length of that string equals 1/2 of my wavelength. Here, for the first harmonic, if I go from the first antinode to the next one, well, that's a crest to a trough. That's also a half a wavelength. So I would say 1/2 of a wavelength equals the length of this tube. Nice. For the second harmonic, like crest to crest, ooh, that's one. Second harmonic up here, midpoint to second midpoint over, hey, that's one. So other than nodes and antinodes in those positions, you get a lot of similar patterns if it's open at both ends or closed at both ends. It starts to get funky when it's closed at one end and open at another. Because here I'm just going from a node to an antinode, and that's it. So that's just a quarter of a wavelength rather than a half. Here I go from a node to an antinode to a node to an antinode. So that's 3/4 of a wavelength. Yeah. So with these, you actually get no even harmonics. Again, I'm not going to test you on that. I just care about what you can do with that information more than anything else. Cool, cool. And how much do we have left? Oh, yeah, we're totally getting near the end. So like I said before, I already mentioned this, but I put it in the slide anyway. Make sure you can identify how many wavelengths fit and solve it, use it to solve for wavelength values. So if I'm talking about the first harmonic on a guitar string, and I know that my guitar string has a length of 80 centimeters, then that means my wavelength would have 160 centimeters, because 1/2 of my wavelength would equal 80. wavelength would equal 160 centimeters or 1.6 meters. So be sure you can do that for any of these types of patterns. One helpful trick, like I mentioned before, from a node to an antinode is always 1/4 of a wavelength. So if you go back to these patterns, I can always highlight there's a node to an antinode, that's 1/4 of a wavelength. Here's an antinode to a node, that's 1/4 of a wavelength. And here's a node to another antinode, that's another 1/4 of a wavelength. So in total, I've got 3/4 of a wavelength fitting there. You can always use that to help you as well. The speed of sound in air you will need to know how to calculate. We've done it a bunch of times in class. It's just 331 plus 0.6 times the temperature, where T is the temperature in Celsius. So, if you were ever a part of a challenge to break the sound barrier, try it on a really, really, really cold day. Because you will not have to pick up as much speed as if you try it on a really, really, really hot day. If you ever find yourself, hey man, you can't break the sound barrier. Yeah, watch me. We're just gonna have to wait till it's freezing. We talked beat frequency. So this is when you've got two sources of sound playing at once. If they differ by 15 hertz or less, you'll start to hear what's called a beat. That sounds sort of like wow, 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 or wow, 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 wow. The sound is getting louder, then quieter, then louder, then quieter. That's because these two source frequencies are both in phase, and because their wavelengths are similar, they stay in phase and continue constructive interference for a while, but then slowly one stretches out in front of the other. Then they end up perfectly out of phase, where the crest of one is lining up with the trough of another, or so on and so forth. In which case, you get destructive interference. That's where it gets quieter. Then it slowly gets back in phase, and you get constructive interference, and it gets louder again. Then they get out of phase, you get destructive interference, it gets quiet again, and loud and quiet and loud and quiet. Wow, wow, wow. The beat, how often you hear the wow, 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 the beat frequency is just the difference in frequencies between the two sources. That's it. It's the difference in frequencies between the two sources. Right. Which means if I'm playing, let's say, 250 hertz, and I play another note along with it, and I hear 2 beats per second, I could either have that second frequency be 248 or 252. It depends. But I know it's 2 hertz away. And finally, we ended with the Doppler effect. Good old Doppler effect. So your observed frequency is different than the frequency that the source is making if you all are moving relative to each other. So F with a little subscript O, that's going to be the frequency the observer detects. That's the observer's frequency right there. F with a little subscript S, that's going to be the frequency the source is actually making. Just regular old V is the speed of the wave. So if you're talking about the Doppler effect in terms of sound, which is what we've been doing so far, V is just the speed of a sound wave. Cool. We're actually going to move on to light and electromagnetic waves after this. The Doppler effect still works there. In that case, V is the speed of light. So you got to be moving a lot faster if you're dealing with light to get a noticeable Doppler effect versus with sound. Interestingly, if you got the observer and the source moving in the same direction at the same speed, the observer just hears the same sound as if they were both sitting at rest, which is kind of cool. The only part about this that's kind of tricky, that makes this not a simple plug and chug, is determining whether Vs and or Vo are positive or negative. So if I've got here, it's a car heading toward somebody. Hey, and the car's blaring its horn. Um, Identify the direction that the sound wave is moving when the observer hears it. Um, so in this case, it's to the right. That is the positive direction. So that means if the car is heading toward me, it's moving in the positive direction. If it's heading away from me, it's moving in the negative direction. And same thing with me. If I move toward the car, I'm moving in the negative direction, so I would plug in a negative number for VO. If I'm heading away from the car, I'm heading in the positive direction, I'd plug in a positive number for VO. Be aware if it is negative, V minus, like let's say I run toward this car at 2 meters per second. I would plug in -2 if I run towards the car at 2 meters per second. So I'm running in the negative direction. VO becomes -2, and I would get the sound speed minus -2. That would come to V plus 2 as my numerator up here. So just be aware of that. That's definitely the hardest part. All right, so as you study for this test, you've got some resources. Under modules on Canvas, you've got module 10. All my lecture videos are still there. Go back if you want to have a lot of fun looking at me talking about magnetism. And then you've got magnetic field problems and solutions. These were some examples we did before spring break, actually, that might not be bad to go back and look over. You've also got, under module 11, all the videos I recorded. Then if you scroll all the way down to the module, old test solutions in review, the PowerPoint is right there, so you can go back, catch anything you might have missed. Also, last year's test, complete with solutions, is also there. So go back and take a look at that. Not only that, you've got a textbook linked directly from my homepage on Canvas. Don't forget about that. That's a really good resource. Get in touch with other students as you work, or get in touch with me, and I'm happy to answer questions as you go. Thank you all for coming. I'm going to stop recording this thing now. Stop broadcast. No. No, that's not working. Let me go do that.